Hello everyone, I'm Federico. I'm currently doing my PhD at the University of Brescia, but I did my master at the VU Amsterdam, and this was my master thesis over there. So today we are going to talk about voltage glitching Intel microcode. So the idea is to glitch the microcode in order to attack the microcode update. And I'm going to give you a little spoiler. Did it work? No, not really, not the microcode update, but I guess there is still something worth it in this presentation. I hope so. You'll tell me probably. So first thing first, I'm going to start with some basics on modern CPUs. This is probably obvious to most of you here, but it wasn't for me when I first started, so I guess this is more a reminder for me than you. This image first was taken from a presentation by Pietro Borrello. He has done a lot of work, interesting work on CPU internals, especially Intel. So I just stole this image because this is way better than anything I could come up myself. So what we see here is essentially just one core of the CPU, and we can see three main components of it. So we have the front end here on the left, and that's doing the fetching and decoding of instructions. Then you have the out-of-order engine, which is the back end that does the actual execution of anything you give to the CPU. And on top of that, you have the memory pipeline, which is essentially prefetching things and caching the result of execution. What we care about mostly today is the front end, which is, again, doing fetch and decoding of instruction, but in the case of complex CPUs, like especially x86, which has a very complex instruction set, the decoding essentially involves translating the x86 instruction set into something simpler, something that can be implemented easier, it can be easy to implement in hardware, and also it's more efficient. Because in the end, if you don't want to have everything implemented in silicon, because most of the times you have some instructions that are really complex and not very used, like CPU ID is used a couple of times when the computer is booting up probably, and then never again. So you would be wasting silicon, and you would also be wasting power, because essentially you have these transistors which are always there, and you got to power them on for no reason. So what you do is essentially convert these complex x86 instructions into micro operations, micro ops. You have three ways to do that. You have three types of decoders. Some simple decoders. In this image there are 4, but actually in the CPU I'm going to work on there are 3. And they do one-to-one mapping of simpler extraction, like add, something that has to be efficient and implemented in hardware, essentially. So add is used very often. You want that to be very, very efficient and very quick to execute, so it's going to map one-to-one. Then you have complex decoders that do conversion of instruction that actually require a couple of microinstructions, and the microcode sequencer, which is what we are going to talk about today, that does essentially implements instructions like CPU ID, write MSR, or VM enter, VM exit, stuff that is really complex. It's not used very often, and you don't really care about it being so quick. So the sequencer is if you look at it, it sort of looks like a microcontroller of its own, but it does not do any execution. But still it has ROM, where it can store programs. These programs are the actual implementation of the instruction, actually, in micro operations. Then you have some RAM from which where you can store data, or from which you can also execute more code. So you can essentially write code in RAM and jump there and execute it. Some registers which are exclusive to the microcode sequencer, but of course it can also access architectural registers, because it needs to read data that the user is giving the CPU, or also return the data once the execution is done. And among these registers, it has an extraction pointer, because this thing essentially can just execute loops, and it can branch or whatever. And the most important thing I would say about the microcode sequencer is that it's updatable. So whenever you're running a microcode update, whenever your computer is starting, it automatically applies some microcode updates. The code that's in the update is executed by the microcode sequencer. It could be changing some configuration on some peripherals, or also changing the behavior of an extraction, essentially. Whenever you update your computer, you have essentially there is a way to retrieve the version of the microcode update, and that's essentially patching away the instruction that returns the microcode update version. So now let's make one step back, and let's talk about read unlock. Just like every microcontroller you could think about, they have ways to debug those microcontrollers. The same thing applies to Intel CPUs. Well, actually, the level at which you can debug an Intel CPU if you have engineer access is way more extensive than you could with your run of your standard ESP32 or something. You can debug each and every subcomponent, microarchitectural component of a CPU, going down to the single buffers. But of course, this is not allowed on consumer hardware. Like, technically, everything is there. An Intel engineer can debug the CPU that's currently showing you this presentation, but it needs to be locked down through, well, in the case of consumer hardware, a JTAG password or some software. So you can have some privileged component of the CPU that can write to a register, and then it enables debugging. Something like the Intel ME can do this. And well, when you have software, eventually you will find someone like these three very motivated gentlemen who found a way to exploit the ME on some specific CPUs of Intel, and they were able to enable debugging on the CPU. So what they did, essentially, quick and easy steps. They found themselves an exploit for the Intel ME. They extracted the microcode with once they had enabled JTAG. Now, easy part, they reverse engineered this completely new architecture with no documentation, of course. They had some leaked stuff, but that's not much. And while you were there, they reverse engineered the whole microcode and found that there were some undocumented instructions that allow you to read and write the internal state of the CPU, essentially. And through that, you are now able to write your own custom microcode. There are two projects that do this. One is Custom Processing Unit by the same person, Pietro Borrello, the same person from which I've stolen the first slide. And libmicro by, it's a recent project, and it's developed by a team, people from a CTF team that was playing yesterday, I think. Calma Riunione, pardon my pronunciation. So how do you write custom microcode? How does the microcode sequencer work? Well, whenever the microcode sequencer is invoked, because an instruction has to be decoded by the sequencer, you have a translation table. So the microsequencer finds the instruction within the translation table, and it will start executing from the ROM, so where the microprogram is stored. Whenever you patch something, though, you have this other set of registers, which are called match and patch registers, where essentially you can write an address that you want to be patched, and then the destination of the address where you want to jump to whenever you are hitting this specific address. So essentially, you write your own custom microcode by patching away the implementation of something like CPU ID, and then you write your own custom microcode in the RAM. Now, making another step back, a couple of years ago, it was proven that Intel CPUs, x86 CPUs actually, because I think this applies to AMD as well, are actually vulnerable to voltage fault injection. And the cool part, for me at least, of this attack was that you didn't have to make any change to the hardware of the target that you were trying to attack. Because normally when you're attacking your standard microcontroller, you have to remove decoupling capacitors, you have to connect to a different power supply so that you can inject the glitch essentially. Well, that was not needed here because you have something on every motherboard that does it for you. You can use the PMIC, the Power Management Integrated Circuit, which essentially is what it's used by the CPU to enable all the power saving features. Because whenever your computer is going to sleep, it slows down the clock, of course, and then you can also lower the supply voltage. And that means that you have something that essentially is driving the transistors on the board and can control the voltage that is given to the CPU. And to do this, like to do this attack, there are two main ways. One is software. So you essentially write a specific MSR on in the CPU, and that tells the CPU to inform the PMIC that you want a lower voltage. Or you can connect directly to the hardware. And the second approach was necessary because, of course, the first thing that Intel did as soon as this exploit came out was removing the MSRs, which is a sensible choice. So the researcher just said, well, I mean, we have this external chip that is somehow connected to the CPU. Let's just find the wires that connect them on the board and impersonate the CPU and send command to the PMIC. So through these attacks, it was possible to glitch x86 instructions, like multiplications, for example, or code that was running in secure enclave. So you could retrieve some cryptographic keys from the secure enclave in an Intel CPU through voltage glitching with these attacks. But this begs the question, how about microcode? Can we do the same with the microcode? It's, of course, a different target. It's smaller, let's say. It's a smaller target to hit. But still, maybe it's feasible. And it's a relatively low-effort attack because we don't have to use lasers or something like that. It's just voltage. You have everything on the board. So now, our roadmap for today finally I'm getting to what I did, is finding some compatible hardware that must be read unlocked, and that's going to reduce the pool of compatible hardware quite a lot. And we also want something that has simple I/O, because whenever you're doing glitching, you're attacking this target and you want to know the state of the target. We want to build some software for this thing, because again, when you're glitching a microcontroller, easy, you just have to get the SDK and you have this main loop and you just write your code there. That's not the same thing with x86, because if anyone ever had to bring up an x86 CPU, you know which kind of clusterfuck is booting up an x86 CPU. We have to make it fast, because if you just think about your random computer booting, it spends something like 10 seconds in the BIOS, and that's way too much. We are going to try glitching, so we are going to reset this thing a bazillion times, and we want sub-second booting times. And then we also have to make the custom microcode work, because the libraries I told you about before, they are either an UEFI application, so you still have to wait until the BIOS is done booting, or a Linux userland library. So essentially, you have to boot the whole operating system to do that, and that's not going to work for the same reason I said before. Like, we want this to be fast. Then, once we've done that, we have to port Plundervolt results to our hardware, because of course the voltage glitching attack was never done on this very cheap hardware that we can work on. They attacked full-fledged motherboards like standard Xeon or core or server motherboards. And then, once we have that working, we have some sort of ground truth. We can work with custom microprograms and try to see if we can do anything to our own microprograms. And finally, eventually, if you get there, try and attack the microcode update, which is a microprogram of its own, but a very complex one. Okay, well, we have to pick the hardware, and we have basically two choices, because I'm lazy and I didn't want to re-implement the read unlock exploit myself. So we have the Gigabyte Bricks, which is one of those small single-board computers that you can, like the thing that you snap to the back of a monitor whenever you have to have a public computer somewhere. And that's running on your standard AMD BIOS, it's closed source. And this was where the first proof of concept was released. And the other option is an app squared. It's sort of a development board. It's relatively open. It's one of the very few boards that Intel is actually where Intel is trying to engage developers on. So you have the open source BIOS by Intel. You have coreboot as well. And you also have some nice GPIOs on the side, because this thing is essentially a Raspberry Pi on steroids with an x86 CPU and a GPU. And this was, the attack here was ported by the libmicro people, so the Calma Reunion and folks, so I have to thank them. Now, I hope they are here because I can say thank you to them in person. Now, let's switch to software. Let's see if we can pick which kind of hardware we can pick based on software. When we try to boot any of these two boards, as soon as we enable the read unlock exploit, we see that the boot jumps up to at least like a minute and a half, which is, again, too much. But thankfully, one of these two boards has coreboot. So we can track where the boot is stalling. We can see that essentially the boot is progressing fine until it hits a stop, and it just waits there for a minute and a half. Well, then the simple solution is just move the code to coreboot. Okay, fine, we're good. We have some simple BIOS that we can just play around with, and we have the source, we're good. Once you decided to use coreboot, that means that you have to write 32-bit code. And that's not a problem per se. It would just be a matter of changing the compiler options. But here, actually, we are working with some undocumented instructions. We are using some not known Intel stuff to write the microcode. And these instructions are always used with 64-bit registers. But of course, they're not accessible in coreboot. So, well, let's just port micro to work in 32-bit mode, because there were some hints that this could possibly be done in the first original paper where they presented these instructions. Maybe you can make this work, nice. And once you've ported it, you notice that you can just, oh, well, I'm done, I can just snap my code wherever I want. Well, no, because if you do that too early, the CPU just dies on you without giving you any exception or anything like that, which is very nice. And then you have to debug this for like a week without figuring out what's the problem there. Well, it seems that you just have to find a stable instruction, a stable point where you can inject your custom microcode. And how would you do that? Well, since I am a joker, I did that manually. I spent a week compiling coreboot with my code in random points, flashing it to a small EEPROM, moving the EEPROM to the target computer, and trying to see if it booted. It was not my finest moment, I've got to be honest. But yeah, essentially you end up with something like this. During the coreboot boot, you have somewhere near the end of the RAM stage, you can now finally have your custom microcode loaded and the board is stable after something like 700 milliseconds, which is good enough. We are within the one second boot time that we expected and we needed. Okay, we good. We got our own software setup, so we now have a target that we can attack. But now we have to think about the voltage glitching, because of course, this hardware has never been proven to be voltage glitchable. And while this is relatively simpler than the read unlock part, this is not a given, because every board has a PMIC, but not all PMIC are made equal. On your gaming motherboard, you might have something that scales up the voltage very quickly, while on this low power board that's only used for IoT, maybe you don't have that. So let's see. Can we also, how do we control this? Like, can we use software? If you read the datasheet for the Intel CPU, which is a very interesting read if you've never done that, it's like 3,000 pages, you learn a lot. You notice that essentially they claim that they haven't implemented software control of the power supply. So software is not going to cut it. Let's go with hardware. That means that we have to reverse engineer the board a little bit until we find where the PMIC is and how it's connected to the CPU. I have to thank Carlo Maragna because he spent a couple of afternoons with me. It was nice to have someone to talk about this with. And while you're there, you can also find vCore, which is the core voltage, essentially, the voltage that you care about. And then you can use that to double check that you are actually changing the voltage of the CPU like you would like to. Now, I'll make a small interjection here because, as I said, not all PMIC are made equal. So whenever you're doing voltage glitching, you would like your glitch to look somewhere like this, something like this. You have your VCC, which is the reference voltage at which the board is operating, and then you have a fault voltage, VF, which can be 0 as well. So you want the glitch to be as narrow as possible. It drops to the fault voltage, and then it goes back straight away to VCC, so that the target will stay operative. It will not die on you, but at the same time, you can inject the glitch. And also, the narrower the glitch, the more precise you will be in injecting your target, your glitch at the moment you care about, essentially. You're not glitching something else completely unrelated. Well, on my board, the glitch looks something like this, which was suboptimal. And this is already too kind. Like, I couldn't represent it because it would have gone beyond the end of the board. It's like 3 orders of magnitude slower than some proper hardware would do it. Okay, let's see. Someone else already had a similar problem, even though their hardware was a bit better. So the Volt Pillager people, they used this two-stage glitch. So essentially, you first drop to preparation voltage, which is stable enough for the CPU to barely stay alive, essentially. And then whenever you need it, you drop to the fault voltage. So essentially, you reduce the perceived width of the glitch, and then you go back to VCC. Okay, maybe this could work. And if you look at it through an oscilloscope, you will see something like this. So essentially, you have the first drop around here, and then it drops again here. So and these in blue and pink, red, are the I2C controls to the PMIC, and yellow is UART, but we don't care about that right now. Okay, now we got the hardware set up. The software is good. How do we inject the glitch? Being a very cheap hacker, I always love the Raspberry Pi Pico because it's so cheap. You can just use anything else. So the Pi Pico has a little issue though, since the system on a chip could actually work at 1.8 volts, but this is a very cheap board, so they didn't bother with having adjustable voltage supplies here. So they only work at 3.3 volts. So what I did was modifying the thing a bit. I desoldered the RP2040, the microcontroller, changed to have a external power supply, cut a couple of traces, and swap this flash. So you can do this. It's actually a nice, interesting experience. You learn a lot about soldering doing this. Now that we got everything, we have to make them talk together. So we now have the target, we have the glitcher. They need to communicate in some way. You have to get the state of the target from the target to the external world, in this case to the glitcher. And I mentioned that our target had very nice GPIOs, but that's not actually going to work because they only work in Linux with a non-upstream driver that loads some custom bitstream into the CPLD, which is a dumb version of an FPGA. I didn't want to bother with any of that, so I just used UART because each and every Intel CPU has one of those old ass UARTs that you will find in the 386. They still have them, and I love them for the backwards compatibility they still keep. So I just made this very stupid communication protocol where you send an R ready whenever you're about to do something on the target. Then you execute your payload, and then D done, and that allows you to check if the target is still alive. If it sends you D done, then you're good, and you can get the output out. OK, maybe this will work. Now, the rest of the setup, well, you just have a host machine that basically orchestrates the whole thing. Laboratory PSU, just your random PSU that you can get on AliExpress, just to power on the board and to reset it whenever the target is not responding anymore. The PC also talks with the PyPico because it needs to get data from the board. So essentially, the board is completely disconnected from the host PC. Everything goes through the PyPico. And then you have your own oscilloscope because why not? Like, you want to see if you're actually doing the things you're supposed to do. And this is a very nice scheme. Everything looks neat, but my personal setup looked more like this. That rat nest there in the corner is the whole thing, essentially. The rest is just, you know, for the kicks. But yeah, it was very nice to explain to people what I was doing when they were walking into my room. Now, OK, we got everything in place. The setup is ready. Let's finally try and see if we can make Plundervolt work. Like, can we get the same results that the original authors? Can we replicate the results? They claim that they were not able to do to inject any fault in simple operations, like additions, subtractions, or logical operations. It was not feasible because they claim these instructions are essentially too small to be targeted. Like, the hardware is not going to be affected by the voltage drop, which makes sense. However, they claim that they were able to inject glitches on imul, so the multiplication. But there are some caveats here. You cannot just glitch any two numbers multiplied together. The operands need to be some specific numbers, and the order of the operands is important. Like 80,000 times 4, that's faulty. 4 times 80,000, you're not going to get any fault with the same settings, and nor with any other setting. And same thing goes, like 80,000, 1, and 4, you're not going to get anything out of it. OK, let's roll with this. Let's try this exact same thing. Now this is probably where I'm going to lose most of you, because personally, whenever I see assembly on slides, I just disconnect. Sorry. But yeah, very simple target. Essentially, you just move the two operands on some registers, then you have two multiplications, and you compare the result of them. You just do a compare, set if the two compares are, like the two values are not equal, and then add one to this ECX register, which is just a counter, essentially, of how many times we have seen a difference, and then just repeat this loop. Normally, like whenever the CPU is running without anything happening to it, we expect ECX to be 0, because that's never going to be the case that two multiplications of the same arguments are going to yield a different result. So essentially, you're always going to add 0 to the ECX register. We expect to see some faults, and then, since we are glitching, and then we would like to see ECX to be greater than 0. And yeah, OK, we can glitch imul, even though the PMIC is not the best. We can actually do that. That's nice. But weirdly, we don't really care about the operand order. Like, wherever, if you swap them, it doesn't really matter. So the question is now, are we actually glitching imul, or are we maybe glitching the comparison? Because technically, the comparison shouldn't be affected by the glitch according to the previous research. But maybe, since we are actually seeing this, maybe that's not the reason. And also, sometimes we get this huge number in ECX instead of just like being 1 or 2. It's 200,000, which is, weirdly, exactly the result of 4 times 80,000. So, and if you look at this code, EDX is used as a destination register for the multiplication. Yeah, by the way, sorry, this is AT&T code. Nobody likes it. I don't like it either, but it's coreboot, so I have to roll with this. And also, like, the same register is also used to do an addition here. So maybe the CPU is actually doing something wrong, and instead of adding just a byte, it's adding the full 32 bits. So okay, maybe something is going on with the register file, since we shouldn't have glitched the CMP, but we are doing this, so maybe there's something wrong with the register file as well. Okay, let's see. Let's see if we can find something new, actually, because these would be new things. Okay, let's just cut down the previous code, and essentially we just do a lot of comparisons and sets. And let's see if we can find anything. Same expected value. ECX is going to be 0 whenever the CPU is running normally. And yep, okay, in 75% of the iterations that we are glitching, we can actually glitch something. And the distribution is also pretty nice, because in blue you can see the expected value, 0. That happens in some instances. Like we are not always lucky. In 25% of the cases we are not. But most of the times, actually, we are injecting a couple of glitches. So maybe we actually found something new here. The compare can be glitched, and that's interesting because compares in x86 are just subtractions. So that means that we are actually glitching basic arithmetic stuff. Now let's see about the register file. You make the code even simpler. Essentially, you just have one value, which is 0101, and then you move a byte. So you essentially are truncating these 0101 to 01. And you move that to B, and then you do an addition. And you just keep on doing that until you're good to go, and then until enough time has passed, essentially, on the CPU for the glitch to be injected. Let's see. Our expected value here would be I, which is the number of iterations, because we are truncating this down to 1, so essentially ECX should be 1. And if otherwise we have managed to glitch the register file, we would add 0101. So we would have now something that's greater than the number of iterations that we are doing. And we don't actually see that, because the expected value, it would be somewhere around here, like 271,000. These are ugly numbers, I know, but still. We expect to see something bigger than that, but actually the values are smaller. And these ones here are also nicely distributed. Like sometimes you can just skip maybe a couple of instructions, but then you have this nice bell curve here. And this hints at, again, like I would say, instruction skips. So we can actually skip x86 instruction probably in this scenario. Okay. Now let's finally move on to microcode, because that's what we care about actually. This is libmicro syntax for microcode. And that's very simple microcode to simply add 1 to the value of RCX and store it into RCX. This is probably the dumbest microcode ever written by anyone. And it does that 10 times in a row, and then returns. That's it. This code gives us essentially two information. Whenever it's running normally, we would see that given I iterations of the code, we would find in ECX I times 10, because of course it has added 10 times 1. But if we can inject some faults, and we maybe are able to skip microinstructions actually, if we find that the result is not the expected one, but it can be divided by 10, then it means that we have skipped an x86 instruction architecturally. While if the result is not divisible by 10, then that means that we have skipped a microinstruction, because somewhere around here something went wrong and we just skipped one of these instead of just the full 10 instructions as a single block. And yeah, these numbers are small, of course, but we are actually able to skip some microinstructions, it seems. Most of the times you just skip instructions, complete ones. The expected value will be 800,000, and most of the times we just get 7999990. But some of the times, yes, we do find that we have skipped one microinstruction here, one microinstruction here, and those are not big numbers. Like it doesn't happen very often, but it does happen. Okay. Now we can move on with the microcode update, which was originally our goal. We have something that maybe we can make this work despite all odds. And this is my understanding of the microcode update, even though I haven't reverse engineered it, because this was my thesis and I wanted to be done eventually with it. So I just got the results that I just went with whatever Pietro said about the microcode update. It's up in his notes on GitHub. So essentially, when you start an update, you pass a file to the CPU and you write the address to the file in some register. And what this does is essentially is checking if the update is valid. So this is only the check that is done by the CPU before the content of the microcode is used. What it does is taking the RSA modulus that's in the file, and it checks if the hash matches with an expected hash. They use hashes because essentially you don't have enough memory within the CPU ROM to store the full 2048 bits of RSA moduluses. So you just store the hash and check that. You check if the exponent matches, okay, fine. You generate an RC4 key with a secret that's partially in the update and partially in the CPU, so it's stored in silicon and never disclosed. And using this RC4 key, you decrypt the content. Once the content has been decrypted, you do a signature check on the content. The process is sound, and of course they're using RC4, which is not the best crypto ever, but they are doing it correctly. They're discarding some data that will probably yield to key leaks. There are not too many microcodes, so you cannot get the key from the microcode itself. They've done their homework. What we see here are essentially two main injection points. Like, you can inject your own custom modulus, but of course the code would fail here. How about we manage to get our hash to be accepted? That would be nice. So we can do our own signature essentially. Like, we can sign our own microcode with our own private keys. That would be nice. And of course, you have the signature check at the end. Let's see if we can attack any of these. So how I did that was essentially measuring the execution time, because the update, it's not constant time. So if it aborts here or it aborts here, there is a clear difference in the amount of time it took to execute the update. So you have a reference time that you get just having an update fail. So essentially, I just modified the signature, and the update would fail after a certain reference time, tref. And normally, you expect the execution time to always match tref within a certain boundary. And of course, if we manage to inject the glitch and get the update to continue longer, we want to see the execution time to be longer than the reference. Okay? And yeah, actually, it's possible to do that. And if you look at this graph, like what I have here is this is an invalid and rejected update. In pink, you have a valid update, but you're updating the same version on top of itself. Like, you have version 20, and you try to install the update for version 20 on it, and it's just going to skip the install step, essentially. And then you have a valid update on top of a new version. Like, you are trying to install version 28 on top of version 20. And after some fine-tuning of the settings, like, you can rather easily get the update to take exactly the same time. However, the update is not working. Like, when you check the version of the update that's actually installed, it always stays the same. And honestly, I don't know why, because it looks so nice. Like, I was so disappointed when this happened. But probably there is something in the update process that's double checking things before it actually commits the result or something like that. Or maybe they're doing the same check on multiple cores. So of course, the second core is going to fault, and then you don't see that. I don't know. But yeah, let's try to see with the update signature. Well, this attack pretty much is the same thing. Like, you just change the reference time, and you just have to change the content of the file. So it's going to reject the update here when the signature doesn't match. And yeah, same thing. And here I had even less luck, because most of the times the CPU just died. And yeah, you have some stuff that it's completely out of the place. So yeah, no dice here. And same thing, the update failed every single time. Now, yeah, that's pretty much what I had for you today. It seems that you can, yes, of course, we know you can skip instructions. We can do, can get simple operations to fault on x86, which is nice. You probably can do something weird with the register file, and you can also skip microinstructions, which is, honestly, it surprised me. I didn't expect that to work. And then you can also change the behavior of a complex microprogram like the microcode update. So you can do something to it. Of course, that's not working right now, but still, like, the fact that it takes more time, that shouldn't happen. As for future work, I would like to reverse engineer the microcode update eventually. Like, I don't really want to, because it's a huge pain to do it, but it might be worth it to do it. And to figure out why the glitch was not enough, actually. And Another option, another interesting thing would be replacing the PMIC, because that thing is very bad. And if we could just power on the CPU on our own, we would be able to get far more precise glitches. And maybe something that came to my mind while I was writing this presentation, actually, there might be a time of check to time of use on the RSA modulus. So if you are able to essentially swap in RAM the code, the microcode, while like after the modulus has been checked, but before it's used to do the signature check, maybe you could change and use and effectively install a microcode file that's not signed. But yeah, that's what I have for you today.
Hello, thank you for the nice presentation. I was wondering, you said that they make a check for the hash of the RSA modulus. What about the exponent?
It's always 13, I think. They also check that. It's in the file, but they check that it matches what they expect.
Okay, thank you.
Hi, awesome presentation. Thank you for the presentation first. When you did the voltage injection, the voltage glitch, have you also checked for any side effects? Because you mentioned instruction skipping, and you mentioned checking like ECX register. Have you also checked all the other registers for making sure like you're bit flipping something and changing the instruction in some other instruction?
No, I haven't, because my final goal was attacking the microcode.
Okay.
So essentially, this was just reproducing some previous work. But in hindsight, honestly, I should have probably focused more on the x86 glitching. Okay. Because probably the reason why in my setup I've seen this stuff, while in previous research they haven't, is that they were attacking a running Linux system, which also means that you have 4 cores running, while in coreboot at this stage I still have only the bootstrap core. So probably I was attacking different things with regards to what they had previously. So probably in hindsight I should have done that. Yeah.
Thank you.
Thank you, Federico, again.